Bismillah ar-Rahman ar-Rahim. The topic that we will be discussing today is deformation under axial loading. As you know that deformation is the change in dimension when the material is subjected to the external loading. And axial loading, by axial loading we mean when the load is along the axis of the material or the mechanical member or component. So in order to discuss this, let's say that we have um, a material in the form of a rod. The length of the rod is L. One end of the rod is fixed, whereas the other end is free. And assume that the cross-section area of the rod or this component is A. So when we apply an external load P on this end of this rod, so it means that we are applying a pulling load. We are applying a pulling load on this rod or material, as a result of which this rod would elongate. The length of this rod would increase, and this increase in length, that is elongation, is, let's say it is delta. So the discussion is that how to find this delta mathematically or analytically. So under this topic, we want to derive a mathematical model with the help of which we could find out delta when we know the external load and the geometry of the material. As we discussed before, that when we apply material to external loading, then two things would happen. First, because of the external loading, the material will resist the external loading, and because of which we come up with the concept of stress. So here, as this load is perpendicular to the resisting area here is the cross-section area of the material, and the load is actually perpendicular to that area. So meaning that we are discussing, or we are dealing with the problem of normal stress and normal strain. And as we discussed before, that when there would be external loading, there would be stress. Stress, as we discussed before, is the resistance of the material against the externally applied load. And we already discussed the Hooke's law. So the Hooke's law says that the stress is directly proportional to strain. Epsilon is the strain. Epsilon is the strain which is produced due to this external loading. And if we want to replace this sign of proportionality by the sign of equality, we have to introduce the constant of proportionality. And in this case, the constant of proportionality is actually E, which is the Young's modulus, or modulus of elasticity. And this key actually represents the stiffness of the material. So by Hooke's law, here we could write down that the normal stress sigma is equal to E epsilon, where epsilon is the strain. Previously, in previous classes, we come up with this mathematical model for the normal stress, which is sigma is equal to external loading divided by the resisting area. Here, the external loading is P, whereas the resisting area is A, so sigma is equal to P by A. So in this equation, instead of sigma, we could put P by A. So the equation would become epsilon is equal to P E by A. And by the definition of the strain, change in dimension per unit original dimension. Here the change in dimension is delta, and the original dimension is L. So by the definition of the strain, epsilon is equal to delta by L. So we have two equations for epsilon. One is from the Hooke's law, and the other is from the basic definition of the strain. So by equating these two equations, if we equate these two equations, so we could make another equation, and that equation is delta by L. This delta by L is equal to PAE. We are trying to find out a mathematical model for delta, so we have to bring this L on the other side of the equation. So multiplying on both sides by L would lead to the equation or the deformation, that is delta. So when by doing that, delta would be equal to PL by EA. Now, so we have the mathematical model for the deformation in terms of the external loading and the geometry of the material, that is length of the rod and cross-section area of the rod, and the material property, which is E. So this is the mathematical model. So we could use that mathematical model to directly find out the deformation by knowing the load, length, cross-section area, and the Young's modulus of the material. In this case, we took only one rod, which is actually of uniform cross-section area. The diameter is constant throughout. It is a uniform material. Also, the material is homogeneous and isotropic. So, what would be in the deformation in rods where it is made of composite materials? It is the combination of a number of materials. Let's say here, you could see that we have a rod. It is made of aluminum, bronze, and stainless steel. Moreover, the diameters are different. Also, the lengths are different. Furthermore, it is also possible that we are applying loads on each and every segment. So in that case, what would be our equation? So in that case, basically the total deformation would be the sum of individual deformations that may occur in individual um segments of the rod. So we would have delta for this, delta for this, and delta for this. And we have to algebraically add all those delta in order to get the overall deformation. So the overall deformation would be delta in rod 1, delta in segment 2, and delta in segment 3, and so on. So generalizing this equation for a number of segments. So we are trying to write this equation in sigma form. So delta is equal to sigma I Pi Li Ai Ei, where I stands from 1 to any number, the number which is actually there in the your material, the number of segments that are included in the material. So generally we have to use this equation. You could write down this equation for any case. If you have 2 segments, you have to consider these 2. If you have 3 segments, you have to write down this equation as. In case if you have more segments, further on, you could also expand the equation. So based on the discussion that we have did, so let's further solve a simple problem with that, so that it become more clear to you that how we could use the mathematical model for the deformation, and we could find out the overall deformation when the material is subjected to external loading. So here what we have a rod, and this rod is not of uniform cross section. The diameter is different. Here the diameter is more, it is capital D, and it is 1.07 inches. And here the diameter is small d, and it is 0.618 inch. The material of the rod is same. Young's modulus is given. It is E is equal to 29 into 10 raised to 4 minus 6 psi. And the problem is we have to determine the deformation of the steel rod shown under the loading. What are the loads? One load is exerting here, is exerting here at the tip. It is 30 kilopascals. At this point, we are exerting the load which is acting towards the left, 45 kips, and this load is 75 kips. These lengths are given. So solution, how to solve such problems, we have to divide the rod into components at the load application points. Then we have to apply a free body analysis on each component to determine the internal forces. And at the end, we have to evaluate the total uh, deformation or deflection in each segment of the rod. So let's start the problem. So we have to take sections. With sections and then freeware diagram, we have to solve this problem. So first of all, what I'm doing, I will take the section. First section, I'm taking a section here. And second section, this section would work from here to here. And then I'm taking the second section here. So this section would cover this load and this load. And thirdly, we would take the third section here. So for this section, if I take this section, we are assuming or visualizing that we are cutting our rod system here. So we are considering the right hand side of the rod. So this is the right hand side of the rod. Here you could see the same load which is acting. This load is acting. This is 45. This load is acting. So what we could see that there could be a load in this direction. We don't know at the moment. We don't know the direction, but just I'm taking that this load P1 is acting in this direction, and our actual system is in static, it is in equilibrium. So it's each and every component would be in equilibrium. This section should also be in equilibrium. So if this is in equilibrium, then we could apply the equation, that is the laws of equilibrium, the two equations of the equilibrium, that is summation of all forces is equal to 0 and summation of all moments is equal to 0. Here we would be using the summation of all forces is equal to 0. So let's apply this condition of equilibrium, sigma f is equal to 0 on this section, section 1. So I am taking the loads which are acting towards the left as positive, so P1. This load is acting towards the right, so I'm taking this as negative, so minus 75 plus 45 and minus 30, and algebraic sum of all these loads must be equal to 0. The only unknown is P1, so from there we could calculate P1. Second, and that P1 after calculation, it would be 60 into 10 raised to power 3 pounds or 60 kilopounds. Secondly, if we take section 2, so again I'm considering the right hand side of the section, and again we are just assuming that a load is acting here in this direction, because the system must be in equilibrium. It must be in equilibrium. So we are assuming that a load P2 is acting in that direction. At the moment, we are not actually talking about the direction. Once we do the calculation would correct us the direction. So again, I'm applying the condition of equilibrium on this segment. Sigma f is equal to 0. So P2, I'm taking this direction as positive. So plus P2 plus 45 and minus 30 is equal to 0. And the only unknown is P2. After calculation, we come up with P2 is equal to minus 15 into 10 raised to power 3 pounds. Negative sign shows that the direction of P2 is in this direction. It is towards right. It is towards the right. We have taken towards the left, which is not correct. So the calculation has corrected the direction. So you could correct the direction. Minus also means compression. Plus sign here means tension. So similarly, taking the third section and considering the right hand side of the section, and I'm applying here, I'm considering the load P3 here. Again, we are applying the condition of equilibrium, sigma f is equal to 0. So according to that, P3 minus 30 is equal to 0. So P3 is 30 into 10 raised to 4 pounds. So now we have calculated or computed these loads P1, P2, and P3. So the model that we have developed is delta is equal to sigma I EI LI AIEI. So first we have to expand this equation for our problem. Here we have three loads, so we have actually uh, expand this equation in three terms. So we would have P1 L1 E1 A1 plus P2 L2 E2 A2 plus E3 L3 E3 A3. The material is same. The material is same, so E would be same for all closed material, for this rod and also for this rod. So taking this E common, so we could take this E common because the material is same throughout for the rod. And the remaining the cross section areas are given. A1, A2, A3 these are given, lengths are given, and loads we have already calculated. E is given. After plugging that, the overall delta is plus sign. Overall, there would be elongation in the material. Plus sign here means there would be elongation in the material. And how much is the elongation? 75.9 into 10 raised to minus 3 inch. So this is the overall deformation in the material because of the loads, external loads, 30 kips, 45 kips, and 75 kips. Now coming the knowledge which we have gained based on that, we are trying to solve another problem so that things become more clear to you. The problem is a little bit complicated than the problem that we discussed before this one. So here you see a mechanism. You see a mechanism composed of links and joints. So here you see one link. The link is BDE, and another link is CD, and another link is AB, and they are connected with joints. So we have a link and joint mechanism. These links are fixed here, whereas these links are connected to the main link BDE. The dimensions are given, and at the tip of this link, a load of 30 kilonewton is applied. So let's first read the statement, and then we will try to simplify the problem, and we try to solve it. So the rigid bar BDE is supported by two links A, B, and CD. So we have a rigid bar. Rigid bar, it means that there would be no deflection. So we have to assume no deflection in this member or link. Rigid means material which is very tough and no deflection may occur if we apply the load. So this is a rigid bar. However, these two links are not rigid. Deformation or deflection may occur in these. Link AB is made of aluminium. Young's modulus is given 70 GPa and has a cross-sectional area of 500 millimeter square. Link CD is made of steel. This link is made of steel Young modulus is given, and similarly the cross-section area is given. For what we have to find for the 30 kilonewton force shown, determine the deflection A, deflection of point B. We have to find the deflection of this point B. Deflection of point D. What is the deflection of point D? How much this point would move as a result of this load? So we have to find this. And number three, we have to find the deflection at point C. So this is actually the problem. We have to find the deflections of these points when a load of 30 kilonewton is applied. So again, we have to use the free body analysis in order to solve the problem. So we have to free body analysis, as we know, we have to separate each and every member of the system from each other, and we have to show the forces, the external forces and the reaction forces on each member of the system, and then we try to solve the problem. So we have to evaluate the deformation of length A, B, C, D, and the displacement of point B and D, etc. At the end, we have to use some geometry and trigonometry to solve the or find out the displacement of point E. So actually, let's visualize what would happen. So if I'm applying a load here, so what would happen? We could visualize that this end would move in the downward direction, whereas this end would move in the upward direction. Or this end would move also. We are assuming that it would move slightly in a down direction. We could visualize that this link would be in compression, and this link would be in tension. So this the new position after the application of this rod, the new position could be somewhat like this. So we could visualize even that what would be the position or what would happen to this link during this application of loading. So let's first, since we would be dealing or handling this problem with freeboard diagram, so we are separating each and every link from each other. So I'm separating the rigid link. The external load here is 30 kilonewton. We could easily assume that the link CD would apply a load on this link, and similarly the link AB would apply a load on this link. Forget about the direction. Just arbitrarily, we are taking the direction because by applying the condition of equilibrium, the equation would correct our direction. So let's say that this force is in this direction, the load at pin or joint D is in this direction, which is actually coming from the link CD, and this force is coming from link AB. It is also in this direction. So this load is given. It is 30 kilonewton. We have to find this load and this load. The system is in equilibrium, so we could apply the condition of equilibrium. That is the first condition of equilibrium and the second condition of equilibrium. The second condition of the equilibrium is the summation of all moments must be equal to 0. So I'm taking summation of all moments at point P is equal to 0. We are taking the summation of all moments at this point is equal to 0. The sign convention, we could take the clockwise movement as negative or counterclockwise as negative. It completely depends upon you. Here I am taking the clockwise movement as negative and counterclockwise as positive. So taking moment at this point, this load would produce a clockwise movement, and I'm taking clockwise minus 30 kilonewton into perpendicular distance. And the perpendicular distance is 0.4 plus 0.2 is 0.6 meters. So this is the moment which this force is producing about this point B. Similarly, the moment produced by this force is counterclockwise, making it positive FCD into perpendicular distance 0.2 meters. This force is not producing any moment. The reason is that it is passing to the point of rotation. The perpendicular distance is 0. So if you take this force FAB and multiply by the perpendicular distance 0, so again we will get 0 here. So there is no need of taking this in consideration. And the summation of all moments is equal to 0. The only unknown is FCD. So after calculation, FCD is equal to plus 90 kilonewton. Plus sign means that the direction which we have taken is correct. So the load is acting in the upward direction. Applying again the condition of equilibrium in order to find out this force AB. So secondly, I'm taking the moment at point D. The summation of all moments point D is equal to 0. So at this point, this load is again producing clockwise moment, so minus 30 kilonewton multiplied by the perpendicular arm, and the perpendicular arm is 0.4. And this force is producing clockwise moment about this point. So again, minus FAB times perpendicular distance, which is 0.2. So minus FAB into 0.2. And after calculation, FAB is equal to minus 60 kilonewton. This minus sign indicates that the direction which we have assumed is not correct. We have to reverse the direction. We have to reverse the direction. And we could also see here, if this is the point of rotation, the external load is acting on this direction, it is producing clockwise movement. So this load should be in the downward direction here, so that it produces the moment in the opposite direction, that is counterclockwise. So correcting the direction. So let's we corrected the direction. So FAB is in the downward direction, FCD is in the upward direction. The magnitude of this is 90 kilonewton. The magnitude of this is 60 kilonewton. So now what I'm doing, I'm now bringing the link AB here. We have separated these links from each other. The force which the link is exerting on the joint, it is FAB. Conversely, the joint would exert the same load, same magnitude of load on the link AB, but in the opposite direction. Reason is the Newton's third law of Newton's third law of motion. For every action, there would be a reaction equal in magnitude but opposite in direction. So these two bodies are actually exerting force on each other. The magnitude is same, but the direction is opposite. So on the pen, the direction is in the downward direction. So on the joint, that is, sorry, on the joint, the direction is in the downward direction. So on the link AB, here or at this point, the direction would be in the opposite direction. Now we have to make the whole system is in equilibrium. Each and every link must be in equilibrium. So if one load is acting at point B, it is acting in the upward direction. So in order to make it in equilibrium, so there would be another load which would be acting at point A, and it would be in the downward direction. The magnitude would be the same because it must also be in equilibrium. So now you could see that this link AB is under compression. The load is compressive loading. So what would happen because of this loading? Deformation would occur. There would be shortening in length of this link. Now let's also make or draw our second link CD. So this is the load which this link is exerting on the joint D. Joint D would exert the same amount of load at this point D of the link, but the direction would be opposite. So FCD is 90 kilonewton. The direction is opposite. And second, then make this link is in equilibrium if load FCD is acting on the downward direction. So at this point C, the load would be in the upward direction. After doing that, if you look at this link is in tension, and because of that, the length would increase. The deformation would be positive. There would be elongation in the link. So up till now, we have calculated the loads, and we have seen that which link is subjected to compression and which link is subjected to elongation. Now next we have to find out the displacement of point B and displacement of point B. Displacement of point B, for we would consider link AB. Model delta B is equal to PLAE. We have already discussed that. We know the length that is given, E is given, cross-section area is given, the load which this link is subjected, we have already computed that is 60 kilonewton. After putting those values, minus sign means compression, minus sign means compression. After putting all those values and then after calculation, we get minus 514 into 10 raised to minus 6 meters. And this negative sign shows shortening of the length of AB. So delta B is actually 0.514 millimeter. Displacement of point D. Same mathematical model, delta D is equal to PLAE. All values are given, or we have already found out or calculated the load in our this link. After putting that, delta D is equal to 300 into 10 raised to power minus 6 meter. So we calculated the displacement of point B, displacement of point D. Next, we have to calculate the displacement of point E. So delta D is equal to 0.3 millimeter. So next we have to compute delta E, that is displacement of point E. So this is our actual problem. And as we discussed in the beginning, that so if we apply a load here, what would happen to the position of this link? So this would happen to the position of this link. This end would move here, the point E would move here, and it would, let's say it becomes E dash. The point D would move and it would become E dash. And point B would move up and it would become B dash. So this is the initial position of the rigid rod or link, and this would be the position when the rod is subjected to the load 30 kilonewton. So here we are getting some sort of geometry, and we will be using this geometry in order to find out the delta E, the displacement of point E. So this is our actual problem, and this line DE represents the initial position of this link, rigid link, whereas after the application, the new position of the link is B dash, B dash, E dash. This displacement B dash is actually delta B, which we have already calculated. D dash, this displacement is delta D, which we have already calculated. We want to calculate this. This distance dt, it is given, it is 0.2 meter, and this distance, that is from B to E, it is also given, it is 0.4 meter. Now actually we don't know this point D, point H. The point H is actually the intersection of these two lines. If we go back and again see, these two lines are intersecting at this point, and we are calling this as H. Let's say uh, that this displacement HD is X. So we know that we know this actually distance, that is 200. So this would be 200 minus X. So in this right angle triangle, this is 200 minus X, this is X. Now we would be using this geometry. We would be using this geometry and some trigonometry. Tangent theta, as you know, that tangent theta is uh, perpendicular base. Let's say this angle is theta, so this angle would be also theta. So in this right angle triangle B dash HB, this is theta. So in this small triangle HB T dash, this would be theta, and also in this bigger triangle HE T dash, this would be theta. So tangent theta in this triangle, the perpendicular is B dash, and the base is VH. We are considering this triangle, BH dash. So tangent theta is B dash VH is equal to. Now look at this small triangle, right angle triangle. D dash H, this angle is theta. So this is perpendicular. Perpendicular is D dash, and the base is HD. So D dash by HD is equal to, now look at this bigger right angle triangle HE dash. So here tangent, this angle is theta. So perpendicular is E dash, base is H E. So now we have equation. Actually, we have three equations. One is this equation, and the second is this equation, and the third is this equation. So we have to utilize all these three equations, and somehow we try to first find X and then delta E. So considering this part of the equation, so I'm bringing this term on this side of the equation, and we are trying to bring BH on the other side of the equation. So utilizing that equation, B dash, it is delta B, we have already calculated. D dash, we have already calculated, it is delta D. BH is X, that we need to BH is 200 millimeter minus X, and HB is X. So we got, after putting the values, we got this equation. The only unknown in this equation is X. So you could very simply find out X. So after calculation, X is equal to 73.7 millimeter. So next I am using this part of the equation. So E dash, and bringing this part on this side of the equation. So divide by E, D dash is equal to E. We bring this part here, so EH divided by HD. And then plugging the values, E dash, we is the delta E. which we are trying to find. TD dash delta D already calculated 0.3 millimeter, and HE is PE plus X. So DE is 0.4 meter, that is 400 millimeter, plus X is 73.7, and then HD is X, so 73. If you look at the equation, the only unknown in the equation is delta E. And after calculation, delta E is equal to 1.928 millimeter. So the conclusion of today's lecture is that if in the beginning we come up with the model for the deformation, that is delta in terms of load, the geometry of the component, and the material property of the component, and we utilize that mathematical model, and we solve a number of problems. Thank you very much.